Greetings, everyone. Today we're going to talk about rational exponents and radicals. We're going to explore how they're related. You'll definitely want to take some notes, especially of the examples, and then also have your calculator present so you can see how to utilize it with rational exponents and radicals. Let's talk about a new notation, radical versus rational exponents. Remember that the checkmark symbol itself is called the radical. The number underneath is called the radicand. And the number out front is called the index. When we have a number with an exponent, it's still called the exponent, but we're going to refer to it as a rational exponent. Let's explore how roots are related to fraction rational powers. For example, the first one, 25 to the 1/2. To the 1/2 is actually saying 25 to the radical with an index of 2. Now, typically we don't actually write the index number when it's a 2. We often just see it as radical 25, which in this case would be 5. All of these are going to be to the 1/2 power. Therefore, they are all going to be square roots. So if you notice, to the 1/2 power is the same as a square root with an index of 2. What happens, though, when we end up with the 1/3 power? That changes our index number. This becomes 8 with a radical, but now our index is 3. Cubed root. What that means is what number times itself gets me to 8. 3 times. Therefore, my solution is just going to be 2. Let's take a look at 64 to the 3rd power. I would rewrite that as 64 to the 3rd root. That 3 becomes my index. What number times itself 3 times gets me to 64? And in this case, it would be 4 times 4 times 4. So the cubed root of 64 is 4. Let's take a look very specifically at how they are related and what they look like next to each other. If I have the rational exponent of 1/2, that means it's a square root and therefore would look like the square root of x. If I have the rational exponent of 1/3, that would mean I have a cubed root. Therefore, my index would be cubed root of x. If I have a rational exponent of 1/4, that would be the 4th root. My index would then become 4. As you can see, we could continue this pattern all the way through to infinity. You'll notice that all of those previous examples had 1 in the numerator. So what happens when the numerator is a number other than 1? Well, I can break this example apart. If I take 2/3, that would be the same as saying 2/1 times 1/3. Therefore, I could rewrite this as 8 squared to the 1/3 power. There's our rule of power to a power. This makes more sense. I could take care of the 8 squared, or I could take care of the 1/3 first, because it could also be written as 8 to the 1/3 squared. We can flip those power to a power around because they're being multiplied. But we want to think of these fractions as separate values. Here's the official rule. If I have a variable or a value to the m over n, the n becomes your denominator. The m becomes the overall exponent. Well, based on our previous examples, we know that the denominator becomes our index value, whether it be cubed root, fourth root, fifth root, and so on. And the m remains our exponent, and we will deal with it as we have dealt with exponents for the last week. Let's take a look at a few examples to see how this rule applies. For this first example, if I break it apart, the 1/2 can be 1 over 1 times 1 over 2. This becomes my exponent, and this becomes my index. Therefore, I have 7 to the first power with an index of 2. To the first power, of course, would be itself. There is no perfect square root of 7, so I would leave my solution as is. This next example, 4/3 can be broken down to 4 over 1 times 1 over 3. The 4 becomes my exponent, the 3 becomes my index. Therefore, I have 4 under the radical with an index of 3, so it's a cubed root, all to the exponent of 4. If I take a look, 4 is not a perfect cube, but I can take 4 to the 4th power. 4 to the 4th power would give me 256. In this case, 256 is not a perfect cube. So for right now, I'm going to leave my solution as is. 2 to the 5/3. Let's shorten this up a little bit. If I notice the pattern, 5 is my exponent, 3 is my index. 2 under a radical, 3 is my index, 5 is my exponent. 2 is not a perfect cube, but I can take 2 to the 5th. 2 to the 5th would give me 32. 32 is not a perfect cube either, so I'm going to leave that as is for right now. Let's take a look at another one. The numerator, if I follow the pattern, becomes my exponent. The denominator, my index. This time I have 7 cubed root 4th power. 7 is not a perfect cubed, but I can take 7 to the 4th power, which would give me the large number of 2,401. Six to the 3/2. 3 is my exponent, 2 is my index. I have radical with a 6. I can put 2 as my index, but we know that that's just our standard square root that we're used to. To the 3rd power. 6 is not a perfect squared, but I can take 6 to the 3rd. 6 to the 3rd would give me a large value of 216. One more example. 1 is my exponent, 6 is my index. I have the 6th root of 2 to the 1st power. Well, to the 1st power is itself, so in the end, I have the 6th root of 2. So again, pay attention to that pattern. The numerator is my exponent. The denominator is my index. This time we want to write the expression using rational exponent notation. That means I want to go from a radical to an exponent. If there's no index identified, we know that it's a 2. That's our sort of standard square root we're used to. Remember, based on our pattern that we just wrote down, the numerator is my exponent and the denominator is my index. Keep following that pattern. So in this case, I have 10 to the 3 halves. Index is my denominator, exponent is my numerator. Here I have 2 to the 1/6. Here I have 2 to the 5/4. Here I have 2 to the 1/3. Here I have 10 to the 1/6. And here I have 10 to the 7/3. So notice that pattern. The index is always the denominator. We can rely on that pattern when we go back and forth. Let's take a quick moment to explore how to use these functions on our calculators. A lot of times we know what the perfect squares and cubes are, but we're not sure of the larger values, or if we have a value that isn't a perfect squared, cubed, fourth root. We can also find the decimal values. Let's take a look at using our scientific calculator. If I want to evaluate a number to a certain power, for example, 256 to the, I use my exponent key, to the parenthesis, and let's say I want to go to the 1/4. 1 divided by 4, close parenthesis. That would give me my fourth root of 256, which is equal to 4. Let's try another one. If I wanted to try 32 to the 1/5 to the parenthesis 1 divided by 5, close parenthesis, equals. The fifth root of 32 is 2. I also might have a key that has a radical with an x value. You'll notice I'll access that if I press second and the exponent key. So for example, if I wanted to take the fifth root, I would type 5, second, exponent key. And let's say 32. I can get the fifth root of 32 is 2. So this is going to be the primary key that you use over and over again with radicals and exponents. Let's take a look at the functions of a graphing calculator. Similar to the scientific calculator, I have an exponent key. So for example, if I want to use 256 to the parenthesis 1 divided by 4, close parenthesis, I get 4. The fourth root of 256 is 4. Similarly, I could do 32 to the 1 divided by 5 and get 2. I also can use the root key, but it is hidden under the button for math. So if I wanted to do the fifth root of 32, I would type 5, math, go down to math option 5, where there's an x and a radical. That now created 5 as my index number. If you have the updated version, it looks very neat and tidy with the radical symbol. Type in what you want under the radical and press equals. We also get 2 this way. So your two main keys are going to be the exponent key and your math key, option 5. What if you're asked to evaluate without a calculator? Well, then you're going to want to use your perfect roots table, which has been provided to you in class. Make note that you will not be allowed to use this roots table on a test if there is any writing on it. So keep it clean. The only thing that should be on there is your name in case you lose it, but do not add any notes or additional writing. Let's explore how to evaluate without a calculator using our perfect roots table. Let's start off by rewriting our first example. Remember, 2 becomes your index, 3 becomes your exponent. Another little trick that I use, it's in alphabetical order. E comes before I. The 3's on top, the 2's on bottom. That might be a little trick to help you out. If I rewrite this, it becomes 25 to the squared root to the power of 3. Well, I know just by looking that 25 is a perfect squared, which takes me to 5. So the square root of 25 is 5, and I still have that third power. If I go from 5 over to the cubed roots, I end up with 125. So this table works for powers and for roots. Let's look at another example. The first thing I notice is that this is a negative exponent. Automatically, that means that that needs to be moved to the denominator. When I move it, it becomes positive. Take care of those basic rules first. The 3 is my index, the 2 is my exponent. So let's rewrite. I have 125 to the cubed root with a squared. If I look down the cubed column at 125, that would give me a value of 5. I haven't dealt with the squared yet. 5 squared, if I take a look at the 5 and I go to the squared column, I get 25. Note that if this is a calculator section, you could also use your calculator to check to see if it's equivalent. Let's take a look at just 2 more examples before we finish up. Again, we're going to evaluate without a calculator. The first thing I make note of on this example is we have a negative exponent. So I'm going to take all of that value that is to the negative exponent and put it under the value of 1. I'm moving it to the other side of the fraction bar. Next, if I take a look at the 5th root of 32 on my table, I end up with a value of 2. I haven't dealt with the squared yet, so I'm going to carry that over. And as we know, 2 squared is 4. Our last one, we have a positive power, so I'm going to leave it as is. I'm going to look at the index value first. If I have a cubed root of 27, that gives me a value of 3. I haven't dealt with the squared yet. But be careful, this is a negative 27. When you have an odd index number or an odd exponent, you keep those signs. This is something you definitely double check on your calculator during work time, but be prepared to deal with it without a calculator. We know that when we square a negative, it becomes positive because a negative 3 times a negative 3 gets me to positive 9. Take your time with these examples. You'll notice that the algebraic piece is pretty simple mathematically, but the rules and the steps are easy to get lost in. So take your time, and we'll see you soon.